All right, what's up, everyone? So now we're going to talk about some surface currents. We've talked about the thermohaline circulation, we've talked about the density movements, and now we're going to focus on what's happening here at the surface. So there's this really cool video, a little TED Talk here, saying how currents work, and it kind of brings everything together. And there is a reason why I'm starting with these cute little rubber duckies. And it's because there was a cargo ship that back in 1992 was sunk, and it was taking this shipment of rubber duckies across the Pacific Ocean and sank. And when it sank, all of these rubber duckies were distributed and were being found on shores all over the world. And so what it did is actually kind of gave scientists a better understanding of surface currents, but it is just kind of a funny little thing that happened. So we have basically two main forms of ocean circulation around the world. One of which being density-driven circulation, that's the thermohaline circulation, right? So that forms at the poles. It's driven by these temperature and these density differences, temperature and salinity differences, which bring forth density. And it moves about 90% of the ocean water, right? So we have to think about the ocean as this three-dimensional object. It's not something that's just at the surface. It has more to it. But then what we're going to talk about now are these wind-driven surface currents. So these are formed at the surface, and they can extend anywhere from just at the surface down to about 1 kilometer's depth. And the reason that there's a variation there will be because winds are sometimes strong and sometimes they're weak. Stronger winds will tend to move and churn around water more efficiently than less wind, right? Think about if you have a cup of coffee or a cup of tea in the morning, and you're out of spoons, but you really love putting creamer in your beverage, and so you put a little bit of creamer in there, and if you just blew on it on like a little teeny tiny little blow, then it wouldn't really move anything around that much. But if you gave it a real nice hard blow out of your mouth, then it would move things around a bit more efficiently. These surface wind currents also tend to follow wind patterns pretty well, and then this idea of movement moves about only 10% of the ocean water, which I think is pretty fascinating. So if we break down what these currents kind of look like, we can make out these major circulations around the world. So we kind of have 5 major gyres around the world, and it basically splits up our oceans. So we have the North Pacific Gyre, the South Pacific Gyre, the North Atlantic Gyre, the South Atlantic Gyre, and the the Indian Ocean Gyre, I should say. But I want to point out that the Indian Gyre really just resides in the southern hemisphere, because most of the mass of the Indian Ocean is in the southern hemisphere. India kind of gets in the way here of what would be a circulation. There's also all these little smaller circulations and smaller currents. Those definitely exist for sure, and we'll learn a little bit later on that there are even smaller little circulations that we observe, but this is just kind of an overall averaged out view of what we would see. And I want to point out here as well is the direction of motion here. In the northern hemisphere, we see this clockwise motion of these circulations. In the southern hemisphere, it's opposite. It's this counterclockwise motion here. And that's because of the Ekman spiral, Ekman transport, Coriolis force, all that stuff kind of put together brings around these circulations here. So there's also temperature involved in the mix. So first, let's look at just the sea surface temperature throughout the whole oceans. And if we were to compare what like the temperature of the oceans at a particular latitude, like say, for example, here in Northern California, at the same latitude, we have the East Coast. And if we were to look at the ocean temperatures at either coast at the same latitude, we can see that the water off the California coast is much cooler than the water off the East Coast. And this actually has some pretty intense climatological impacts. We live here in San Francisco. We know for the most part, if you live right along the coast, that our climate is pretty moderate, right? There's not a whole lot of changes. Our range is pretty small. It stays pretty, temperate. It's quite nice. But if you were to go hang out on the East Coast, you would see a much larger range in temperatures. I tried to show this earlier in the semester when I compared San Diego, Dallas, and Charleston because of that same thing. San Diego's right next to the Pacific Ocean, Dallas is landlocked, and Charleston is over here in Georgia. Sorry, I just had to make a little face there because it's silly. And so that's kind of why we see that there. So if we were to draw those same gyres but add temperature into the mix, this is generally what we would see. So we see these warmer currents on the eastern side of these gyres and cooler currents on the western side of the gyres, oh my gosh, and eastern side of the gyres are cooler. We're going to get into this idea of western and eastern boundary currents here in a minute. And I just flubbed over my own words, as I'm sure you will when you talk about this or when you try to write this out. When we're thinking about these gyres, we have to think about the ocean basins in terms of northeast, southwest, not like east coast of North America being the eastern boundary current and the western coast of North America being the western boundary current. It means in terms of the gyre. And I already flubbed up, so if you flub up on that too, no worries there. But this really just kind of puts all of those things together. And one thing I also just want to point out, which I didn't in the previous slide, I apologize, is the southern current. So the southern ocean current is very, very strong, and it really keeps, for all intents and purposes, the southern ocean kind of separate from everybody else. And this is just putting the wind currents and the ocean currents all on one map here. So it kind of just shows how the winds move the water, essentially. So now we're going to get into this idea of something called Western intensification, and this is kind of a funky concept. So if it takes you a few moments to figure this one out, or if you need a little bit more help, or you need to use different resources for this, I totally get it. It's a funky concept, so have no fear if you're like, what? Because I totally understand. But first we need to understand this idea of something called geostrophic flow. So geostrophic flow is the balance between the force of gravity and the force of the Coriolis force. I told you we weren't going to be done with Coriolis when we talked about it in the atmosphere. It's coming back in terms of the oceans. So what we can see here in this figure on the right is a profile view, so a side view on top, and a map view, which is a top side view on the bottom. So this side view, we can see something that's really quite fascinating, and something we do observe in nature is this literal bulge in the water. So the water is not flat. We can actually see in the middle of these gyres like actual mounds of water from this buildup here. And then if we were to see from a top-down view, notice how there's how these lines, how they're kind of how they are closer together on the left side and further apart on the right side. The closer together these lines are means that there's a steeper gradient. And that's why this arrow is longer here, because with that more intense gradient, the water is moving faster through that channel. Whereas on the eastern side, or on the right side here, the contours are really far apart, and notice how this red arrow is much shorter, indicating a slower flow. And this is really, really important in terms of differing between the western boundary current and the eastern boundary current. Western boundary currents tend to be much, much faster than that of the eastern boundary currents. And there's other things at play here as well. One thing I also want to point out is that the center of the gyre is also not literally in the center of the actual circulation. Notice how it's offset a little bit. Yeah. So just a little bit more on this idea of western intensification and kind of some things that we observe here. On the western boundary currents, we often see a more narrow and a deeper current. Continuing on with this idea of a strong current, whereas with our eastern boundary currents, they tend to be more broad and shallow, and they are also a bit weaker. So western boundary currents also move water more efficiently. They're moving more water in terms of volume. So if we were to consider looking at a map, a topographical map of the oceans, this is for October 3rd to the October 12th in 1992. So I do realize that is a much kind of shorter, kind of time span here. but we can definitely see how there's like this larger mound or a larger hill, if you will, in the oceans by kind of a bit, right? Like 80 plus centimeters. That's almost a meter. That's almost 3.5 feet. Pretty intense over here on the western side. More intense in the western or in the Pacific Ocean than in the Atlantic Ocean, but it is still something that we can see in the Atlantic, both in the northern and in the southern Atlantic. So if we were to put all these ideas together into a lovely table, well, guess what? I love tables, and here's all this information. So for each boundary current, I have this divvied up into location, travel direction, temperature, speed, width, depth, volume, and world examples. This will be something that you see on your final exam, and it will be worth quite a bit of points. As you can kind of tell, there's a lot of information here, but the idea is to not have the actual like hard values. It's more of this idea of, is it slow, is it fast, is it broad, is it narrow, is it shallow, is it deep, etc. So that's kind of the idea here. One last thing I wanted to point out in terms of western and eastern boundary currents is that the Gulf Stream is much, much, much faster than most western boundary currents. The Gulf Stream is unique in that sense, and there could be several reasons for that. I have my own theories, but we'll get to that at another time if you want to have a conversation about it. Then when we have all of these gyres and all of these circulations, there is actually a bit of a consequence to this, and the consequences can be quite dire in that we have now in the middle of our lovely Pacific Ocean, the Great Pacific Garbage Patch. So the Great Pacific Garbage Patch, unfortunately, is imagined this way, and I've always imagined it this way as well, but unfortunately, it actually looks more so like a regular ocean surface. Doesn't look like there's a whole lot going on there, but there's more going on underneath the surface. It's also this issue of microplastics. So microplastics are defined as plastic that is less than 5 millimeters, which is super, super small. And it's broken down from wave action as well as the sun beating down on all of this plastic and breaking it down. So unfortunately, because of the reality of these patches, it does not make sense to go out and clean all of this stuff up. Unfortunately, it's generally more effective to confront the plastic where we encounter it in our lives before it gets to the ocean. There is a lovely group out of, I want to say, Denmark. This gentleman, Boylan Slat, he has this group called the Ocean Cleanup, and they're going and trying to clean up the garbage patch on its own, but they also are deploying different ships that can clean up the plastic at its source in various southeastern Asian countries. So like in Bangkok and in Kuala Lumpur, unfortunately, they just litter a lot, and a lot of plastic makes it to the rivers, which makes it to the oceans, which is the source of a lot of this trash. Not all of it, but a lot of it, unfortunately. And lastly, it's really important to note that most plastic that ends up in the ocean, about 80% of it comes from inland regions. So it's not necessarily the people along the coast that are doing this. It's the people who live in landlocked areas that are just throwing their trash into rivers, and rivers eventually make it to the ocean. So every single human being on this planet can have an impact on plastic pollution. And of course, many sources estimate that the amount of time that it takes for plastic to degrade is still kind of up in the air. But scientists are still, trying to figure that one out. I think last thing I read was like 450 years. It also depends on the type of plastic. Is it really being broken down? Is it really degrading? What's going on here? And, it's still kind of up in the air, which is unfortunate. So do your best and don't be a trash human. It's really not that hard. Trash cans are everywhere. Put your trash in your pocket and do away with it later. All right. Thank you so much for watching. I really hope audio issues did not occur this time.